stage, I would like just to turn to the derivative of an exponential function, which for me is a very important derivative because we're going to use it to derive derivatives like the one for logarithmic function. Let's say y is equals to e to the power of x. Normally, in maths 1, maths 2, we simply say the derivative y prime is equals to e to the power of x. For me, that is not enough because that's not very useful and informing. Now, what I would like to us to is, I would like us to slightly go back to the fact that we say the derivative function is the derivative of immediate function multiplied by the derivative of the argument. In this case here, I would like to say the derivative is e to the power x, which is actually e to the power of e of x multiplied by the derivative of x with respect to x, and this is 1. Maybe somebody might worry, why am I saying something so obvious? But that is very important. Let's see as you go. Let's say now, if I had a function y is equals to e to the power of f of x. Now we're in the situation of a chain rule. If I apply the same principle, now I'm going to say the derivative dy dx is equals to e to the power of f of x multiplied by the derivative of the argument. Because remember, what you must recall with respect to the exponential function is that whenever we differentiate an exponential function, it comes back exactly as it is, and the only new thing is that it's multiplied by it's multiplied by the derivative of the argument. We're still going to enrich this thing later, but for now, let's look at this way. So the derivative of e to the power of f of x is going to be e to the power of f of x multiplied by the derivative of the argument. So an exponential function basically is a kind of an exponential function which comes back in its derivative exactly as it is multiplied by the derivative of its argument. Now, how are we going to use that? Once we've known this kind of a form of a derivative of an exponential function, then we can actually proceed to an exponential function of any base. Like, let's say we got a to the power f of x. Now, because this a is a different from natural base, we might basically like to use another method to arrive at the derivative of this function. Let's say we want y prime. We want y prime. Now, maybe before we discuss that, let me just recap another simple derivative which we also looked at in a very simple way, but it's got a lot of compressed kind of information there. Let's say we've got y is equals to ln of x. I remember very well maths 1, we just learned that this is equal, derivative is equal to 1 over x. Again, here when we write this thing, we now sometimes overlook the information that this is a derivative. It must be multiplied by the derivative of the argument. So we can say derivative of x with respect to x. So now, simple summarizing this in words, we would say the derivative of ln of x is 1 over x multiplied by the derivative of x. In words, we would say if we've got a function y is equal to ln, let's say, of f of x, we would basically come up with derivative of y is equal to 1 over f of x. But when I'm saying 1 over f of x, I'm saying 1 over the argument multiplied by the derivative of the argument. This is how I would equals this. So in this case here, this ends up being 1 over the argument, which is f of x multiplied by f of x prime. Now, when we've got this summary that the derivative of a linear function is 1 over the argument multiplied by the derivative of the argument, then, and also having this equality that the derivative of e to the power of x, the power of f of x is e to the power of f of x multiplied by the derivative of the argument, then we can basically proceed and try and understand this, how to get this derivative very easily. What I'm going to do, let's say now we have y equals to a, any base a is equal to f of x. What I can do here to arrive at the derivative y prime, I'll say, invite all to say, let's say apply ln on both sides of this equation. Let's say ln y equals to ln of a to the power of f of x. Then notice that I've just said ln of y there without using brackets, but I could use brackets. No, absolute values in brackets. Then apply the rules of logarithms. Then this would end up with as f of x multiplied by ln of a. Now, differentiating this ln exactly the way I've done it here, I'll basically have 1 over the argument y multiplied by dy dx. I'm saying dy dx because I know from the initial part here that y in the final analysis is a function of x. So dy dx now is 1 over the argument multiplied by the derivative of the argument, which in this case is going to be ln of a multiplied by f prime of x. Now check that here we're actually searching for dy dx, so that we've got an equation at this stage which has got that dy dx. So we can just make substitute formula and we arrive at the fact that therefore dy dx is equals to y ln of a multiplied by the derivative of the argument. Now, summarizing this thing nicely, we can say that the derivative of the exponential function y is equal to a to the power of f of x is equal to the exponential function itself y multiplied by the ln of the base multiplied by the derivative of the argument. So in this case we'll say dy dx is equal to a to the power f of x multiplied by ln of a multiplied by f of x prime. So I think this is very important to understand how to differentiate the exponential function of a general base a. So like we saw before at the top here, that the derivative of the exponential function is the exponential function itself multiplied by the derivative argument. But at the bottom here, we're saying that the derivative of the exponential function is the exponential function itself multiplied by the ln of the base multiplied by the derivative argument, which means that at the top there, we could actually say this derivative is actually also multiplied by ln of e as ln of the base of that function. But since it's equal to 1, that's why we ended up basically leaving this as e to the power of f of x multiplied by f of x prime times 1, which is the general base. So in general, we can basically say, in general, the derivative of any exponential function is the exponential function itself multiplied by ln of the base multiplied by the derivative of the argument. So I think you notice that what I've been emphasizing on, that always when you differentiate the function, you first of all differentiate the immediate function, in this case which is the exponential function, and you must in the final analysis end up multiplied by the derivative of the argument. That is very important, because if you don't understand that, it will be very difficult to do the reverse process of integration. So let me at this stage look at some, just one or two examples. Let's look at this one simple example. Sorry, y. There's an example there. In this case, we're talking about the derivative of exponential function. Let's say I've got 5 to the power cosine x. According to what we've seen then, we know that this the derivative of this function, y prime, would basically contain the exponential function, the initial exponential function itself, which is 5 cosine x multiplied by ln of 5. But remember, in this case, because it's a multiplication, I can write this multiplication in any order. Ln of 5 multiplied by the derivative of the argument in this case, which is cos, which is going to be minus sine x, multiplied by the derivative of the argument of cos, which is x, in this case dx. But normally this part we don't worry about it, because it's 1. Whenever we multiply by 1, we basically 1 is an identity for multiplication. So simplifying, we'll get this as minus sine x brackets 5 cos x. I'm just putting brackets there not to confuse this part with the argument of sine, then multiplied by ln of 5, which you can also write as minus ln of 5 sine x brackets 5 cos x. What I want you to notice in that example there is that the method, the approach which you follow, the steps which you follow in order to differentiate a general exponential function y to the power f of x, where in this case our f of x is cosine of x. Then you can try yourself the following example: half to the power x squared. Just one example. Another one can write y is equals to 3 to the power tan x, and y is equals to pi x. And similar examples you can find in some other textbooks, just to practice this concept. Now, at this stage, I think now we're also ready to look at the derivative of a logarithm function. Let's say, in this case, this is number 3, logarithm functions. Now, let's say now we've got y is equals to ln of f of x. I'm just going to deal in this case with a natural base. You can devise the other general base for yourselves and see how to differentiate logarithm functions. So to simplify this thing again, I'm basically going to apply e on both sides and say e to the power y equals to e to the power ln of f of x. Basically, the reason why I'm trying to make you understand this derivatives deeply is that when we integrate, we'll need this thing a lot. So if every time we get stuck with the integration, we're going to keep integration, but in the during our course, if you get stuck with integration, you must basically revise a bit of differentiation and integration in order to proceed with some exercises which are challenging. Now, in this case, on the right hand side here, we see that this will simplify to f of x, and this side we're going to have e to the power y. Then if we differentiate e like we saw it before, this will be e to the power y multiplied by dy dx equals to the derivative of f of x, because in this case, at this point here, I'll be differentiating kind of an equation. I'm differentiating both sides. So in this case here, we arrive at the point that dy dx is equals to e to the power y multiplied by the derivative of argument, in this case f of x. Now, so if this is not e to the power y, but e to the power minus y, sorry, which is the same as writing this as f prime divided by e to the power y. Now, but if you look at this stage here, e to the power y is actually the what? The function. E to the power y is actually the function f of x, which is the argument. In this case, then you come back to what you saw before, that this is f prime of x over f of x, which is equals to 1 over f of x multiplied by the derivative of the argument. I think we saw this briefly. Again, just repeating it here to show you that you can actually arrive at it in this way again. So this is very important to master these derivatives. So for examples, I'm just going to give you a few things to do here. Is y equals to ln of tan of x, and you can go to also to differentiate ln of sine of x, and you can also look at something like y is equals to ln of square root of x squared plus 1. Just practice them and master this exercise. So I'm going to stop there in respect to derivative of exponential function and the logarithm function. Thank you.